started. Just a couple of administrative announcements. Let's see. So I will be out of town for a couple lectures later this month. I'll just let you know the dates. So there will be no class on Wednesday, March 16th, or Wednesday, March 30th. But there will be a special secret surprise lecture, if I can spell secret. Special secret surprise lecture by a mysterious guest who will tell you about something that is outside of the standard curriculum of this class, but I promise you is going to be completely fascinating. And that will be on March 28th. So we'll miss 2 lectures. Those are the lectures that I made up earlier this semester. And you'll have a special secret surprise lecture on that Monday. Oh, also, we should talk about the exam. When did they ever officially schedule the exam? Do you know? Is that why you're raising your hand?
No, I was wondering if the surprise lecture is at 8:30 or 9.
The surprise lecture will be at 9, as usual. Does anyone know when they've officially scheduled the exam for? You have a computer. Why don't you look it up? Is it still April 13th?
I think so.
Okay. What's that? So
I think that's still kind of eats into quantum.
Okay. When do you guys have your exams?
If GR is on the 15th.
Well,
then it would be on the 14th.
Your quantum exam is on the 13th?
On the 14th.
Yeah. So we could have. So I think by scheduling it for the 13th, it's supposed to be due on the 13th. So I could hand it out on the 12th, and it'd be due the 13th. Okay. Then that wouldn't present a conflict.
We could do it the day after, for like 13th.
Day after what?
Like 14th evening until.
Yeah, I would prefer to have everyone take it at the same time, to the extent that that's possible. Is there a conflict on?
Oh no, just be.
Okay. How about this? Those people who actually show up to class get to vote on the time and date that the exam is handed out and picked up. When is your quantum exam on the 14th?
I'm going to check that. Or actually, because you have the.
Yeah.
Sorry, what's that? There is an optics exam Wednesday. Yeah. There probably aren't too many. There's probably not too much overlap. Are you? You're in the optics class. How many other people are in the optics class? Maybe what we can do is, if there's only like 1 or 2 people who have a conflict, I can reschedule those. But I would prefer to have the majority of people take the exam at the same time, just because that makes everyone's life easier. Well, by everyone I mean me. Well, it also allows me to focus my energies on answering all of your questions as diligently and as thoroughly and helpfully as possible. So it helps you too. Okay, when is your quantum exam?
It would be, the quantum exam.
Wait, quantum? What quantum are you taking? Oh, U2s. U2s get no consideration. This is a U3 class.
This is true,
But that's right, you are a bunch of U2s. Okay, but you guys are like the only U2s in the class. Okay.
A bunch of us have diff geo on the same day as them.
Differential geometry. When do you have differential geometry?
The same day as them, but in the afternoon.
2 to 5? Yeah. I'd rather not hand out the exam at like 6 p.m. and then collect it at 6 p.m. the following day. Because I have a reason that I want you to not be taking the exam on Friday afternoon, the 15th. In particular, I might as well tell you now, there's a colloquium that I want you all to attend on the afternoon of Friday, April 15th, and I'll give you extra credit. I'll give everyone extra credit in this class who attends this colloquium. Okay. So I don't want the exam to be then, because then that fucks with the incentives. Okay. What's that? Yeah, that seems a little cruel and unusual. How about this? What's wrong with having the exam handed out on the 12th and due the 13th? Except for the quantum people, but there's only 3 of you. We can deal with you guys later. Okay, exam handed out. When is Diff Geo? The 14th, you said? Well, that gives you a whole 24 hours to recover. 26.
What if we don't sleep?
You can sleep. You'll sleep.
You think we will?
Yeah, I won't make it too hard. Well, I did already write one of the questions.
Yeah, last time I said less than 3 hours for it.
Yeah, that quantum exam was a little harder than I thought it would be.
This could be disastrous. Many people said
But yeah, my goal is not to torture you. I mean, if it happens, it's just a pleasant side effect, but that's not my goal. Okay, here. Okay, okay. What would you propose?
after the 14th, or up the day of the 14th.
Okay. Would you like me to hand it? I won't hand it out later than noon on the 14th. For the but you have an exam between 2 and 5.
Yes.
But I suspect that there are a lot of people in differential geometry who would not agree with you,
Probably.
such as the person sitting right in front of you.
I wasn't listening.
But I think he's still not agreeing with you. How about Monday, the 11th?
That'd be okay.
Wait, hold on. Can you bring that?
Yeah.
And
I
then,
have an exam on
What do you
Tuesday
have?
morning.
Tuesday morning. What do you have?
Logic.
Logic. You're probably the only person taking logic.
Yeah.
Okay.
Frank's also in that.
Yeah, but I don't care about Frank. I don't care who Frank. Who is Frank? I don't know. Okay.
11th will be fine for you.
Okay. Let's provisionally say yes. Yeah. In the morning. Okay, but what if I hand it out at noon? Okay? Exam handed out at, so if the exam ends at noon, we could hand it out at 12:30 on April 11th. And collected at 12:30 on April 12th. That will give you a full 48 hours to recover for differential geometry. You could sleep that whole time if you want. And is there anyone here who has a conflict with that? You have a conflict. But we will deal with you separately. Because if we try and schedule around every person who's taking some random class, that will be difficult. But you could, for example, when is your exam?
Tuesday morning. So,
Tuesday morning.
13th.
12:30 on Tuesday?
Yep.
That's when your exam is? Okay, there's not actually a conflict then, strictly speaking. But you could pick it. Okay, we could deal with you separately. Okay. Is there any conflict that anyone knows of aside from logic? Okay. Are you not answering because you just have no idea when your exams are? Okay. How about this? You all have an assignment, which is to figure out when your exams are, and then come back and we'll reopen the discussion Monday if necessary. Okay. Good. Enough of that. Do I have any other announcements? God, I hope not. Okay, let's talk about, one other announcement. By the way, the last problem set was a little on the longer side. The next problem set is also a little on the longer side. It's probably not quite as long as the last problem set, but I would still recommend not starting it the day before, because you might find it a little too lengthy. It's actually a very, very interesting problem set. But I would not recommend starting it the night before. Okay, good. Well, let's do some physics. So today is a very, very exciting day. Because today is the day that we study the Schwarzschild solution of general relativity. So there's been a considerable amount of foreshadowing in this course. So you probably already understand that the Schwarzschild solution is the most important solution of general relativity after the solution of flat Minkowski space. And the Schwarzschild solution is the answer to the question, what is the gravitational field, which is to say the metric around a static spherically symmetric object. Such as the sun or the earth in the approximation that these objects are completely spherical and are not rotating. So let's first, before trying to answer this question in general relativity, let's answer this question in Newtonian gravity. So in Newtonian gravity, we answer this question by solving Newton's equation of motion for the gravitational potential phi. So what is that equation? That equation says that grad squared phi, the Laplacian of phi, is proportional to the mass density which is present. And if we only wish to study the gravitational field outside of the object, so away from the interior of the sun or the earth or whatever object it is we're studying, then we just need to solve the source-free equation of motion, saying that the Laplacian of phi is equal to 0. So that is outside of the object. And because, generally speaking, we'll be interested in the motion of objects which are outside of the sun rather than inside of the sun, this will be the relevant equation of motion to study. Of course, if we wanted to describe the metric in the interior of a star, then we would have to do something more sophisticated, come up with some model for the matter inside the star, and compute its stress tensor before solving the equations of motion. But for the time being, let's restrict ourselves to the very interesting question and more important question of what happens outside of the interior of the sun or the earth or some other spherically symmetric object. Okay, so what's the solution? Well, you all know what the solution to this equation of motion is. Phi will fall off like 1 over r. That's just the usual 1 over r squared force law for gravity. And the coefficient is just Newton's constant, g, times the mass of the object. So phi falls off like 1 over r. So what we would now like to ask, and so, for example, if you were Newton, you could derive Kepler's equations, for example, by studying the motion of objects in the presence of this gravitational field. And we would now like to ask, what are the deviations to those Newtonian answers due to the presence of space-time curvature and due to general relativity? So we would like to now ask, what is the analogous metric which describes the curved spacetime outside of a spherically symmetric object in general relativity? So in general relativity, we need to find a metric which solves Einstein's equations, and in particular, which solves the source-free Einstein's equations, r mu nu equals to 0, and is static and spherically symmetric. And that's what we're going to do today. And in solving Einstein's equations, we will be helped significantly by the fact that we're looking for spacetimes with a lot of symmetry. We've assumed that the object is spherically symmetric, or to a good approximation at least is spherically symmetric. And we've also assumed that nothing depends on time. So that means that we have 4 continuous symmetries of our spacetime. We have one time translation symmetry, and we have 3 rotation symmetries. So what we called an SO3 or SU2 rotation symmetry. This is just the rotational symmetry of a 3-dimensional flat space. Yes?
How does Earth, what motivates time invariance?
Well, so of course, if we are thinking about the sun, for example, then the sun is not something that is time translation invariant exactly, because, the sun is oscillating and wobbling and, in all sorts of interesting ways. And it's also rotating, which, as we'll see in a second, is another approximation. So we'll take the approximation where the sun is not rotating. And so this is just an approximation. Intuitively, I think it should be clear that in a certain approximation, at least, we could think of the sun as an object which is just a spherical ball of some mass, which is just sitting there statically. Now, of course, the sun is oscillating, it's wobbling, it's orbiting around the center of the galaxy, and so that would involve not just some relative velocity, but some relative acceleration in some way. As usual in physics, in order to get a sensible answer that we can really get our hands on, we're going to need to make some approximations. And these approximations are very good ones. So later in this class, we'll start moving away from this approximation. So we'll discuss very explicitly what happens if you allow yourselves to include the effect of rotation. In that case, one can also write down exactly what the metric should look like. If you throw away all of your symmetries, however, that will quickly become a task which is not solvable analytically, and then you'll need some approximation scheme. So right now, we're just starting with the simplest approximation that we can come up with. And in general, the effects of general relativity are quite small. And so all, or the vast majority of the observable effects of general relativity can actually be extracted in this approximation. Not all, but most of them. And when we talk about the experimental tests of general relativity, which is what we'll be spending a lot of next week doing, we'll discuss the various tests that can be derived in this approximation. Good question. Any other questions? Good. Okay. So we have here 4 continuous symmetries, 1 time translation and 3 rotations, and that will constrain the form of the metric considerably. So the fact that we have a time translation symmetry will mean that there is a time coordinate, and the metric will be independent of that time coordinate. And likewise, the fact that there's a rotational symmetry means that there will be the metric of the 2-sphere, the 2-dimensional rotationally invariant metric on the sphere that we met last time, which will also appear as some part of the metric. And the various components of the metric can be put in a coordinate system where they're independent of the coordinates on the sphere. So in particular, what that means is that the metric will take the following form. So there will be a time coordinate, which I will call t hat squared, and there will be a 2-dimensional sphere in the metric. Now, spacetime is 4-dimensional, and I have only accounted for 3 of the dimensions here. So there will be some other coordinate that I will call rho for the time being. And in general, the coefficients of all of these various terms in the metric will be some function of rho. Now, it can't depend on the angular coordinates or the time coordinate, but it will just depend on the rho coordinate. So I'll call the coefficient of dt squared minus e to the 2 alpha. I put a minus sign there because t is going to be a time-like direction. The coefficient of d omega squared I'll call e to the 2 gamma, and the coefficient of d rho squared I'll call e to the 2 beta. And here, d omega squared is the usual metric on the sphere, which we could write in spherical coordinates as d theta squared plus cosine squared theta d phi squared, which is the metric that you have encountered both last lecture and on your problem sets. And I remind you that this metric is the only metric on a 2-dimensional space which is invariant under these rotational symmetries, the SO3 or the SU2 rotational symmetries that describe the rotation symmetries of flat space.
Shouldn't that be signed?
Oh, do you want me to call it sine? I really don't care. Of course, one can always shift theta by pi over 2. and make that a sine or a cosine. So I, will half the time I'll call it a cosine, half the time I'll call it a sine. That's just a coordinate choice. If I shifted theta by pi over 2, that's just a change of coordinates, and then this cosine would become a sine. So in these coordinates, for example, the poles of the sphere, the north and the south pole, are at theta equals pi over 2 and minus pi over 2, where cosine goes to 0, and the equator is at theta equals 0. Do you want to call it pi over 2? No, let's call it 0. Otherwise, I might get confused someday. Hang on. I just want to check in my notes and make sure that when I do these calculations later on. Yeah, let's stick with this coordinate system. Okay. Now, I have actually, if you think about it, so far I've just written down the possible diagonal terms in the metric, but there could in principle also be off-diagonal terms in the metric. And when we consider the metric around rotating objects, those off-diagonal terms will appear. But right now I'm interested in the simplest case where the object is not rotating. And so what I would also like to assume is that the metric is time reversal invariant. So why does this help? Well, under time reversal, angular momentum goes to minus angular momentum. So this means that our object will have some mass, but no angular momentum, no rotation. So, and indeed, you can see that this will forbid the various possible off-diagonal terms in the metric. So, for example, you could first of all imagine that you have some terms that look like a angular direction, d theta or d phi, times either dt or d rho. And those terms can't be there just because of spherical symmetry. Why? If you had a term like d theta times d rho, well, that would mean that from the point of view of the rotational symmetry, you had a vector pointing in the theta direction. And that vector would not be rotationally invariant. In particular, you can show, and I invite you to try and prove this tonight if you're working through these notes, that all of the cross terms d theta, d rho, d phi, d rho, d theta, dt, d phi, dt will violate the SU2 symmetry. You could literally write down the equation that this metric has a killing vector, which are the killing vectors of the two-sphere, and you'll see that all of those cross terms involving the sphere directions will violate that spherical symmetry. So that is not allowed by rotational symmetry. However, there are other sorts of cross terms that we could have. In particular, we could have a cross term which looks like dt d rho. So here we only have a time translation symmetry. T goes to t plus constant. And if we had a term that looked like dt d rho in the metric, so a gt rho term in the metric that depended on rho in some way, that would be time translation invariant. But it is not time reversal invariant. In particular, this term is not invariant under t goes to minus t. You can see that dt d rho picks up a minus sign when you take t to minus t. So if we make the additional assumption that in addition to a time translation symmetry and a rotation symmetry, our metric is also invariant under time reversal, t goes to minus t, then this form for the metric that I have written above is the most general possible form that we could write down. And this will be the starting point for our discussion of the metric around a static spherically symmetric object. And later on in this course, I will present to you, but not derive for you, the metric for a more general object, which is rotating, where we have these off-diagonal terms. I won't derive it for you, but in a later problem set, you will check that it is a solution of the equations of general relativity. Questions? Comments? Thoughts to share with the group? Okay. Now, we have here a metric that depends on three functions of the variable rho. Alpha, beta, and gamma are the names that I have given these functions. Actually, let me rename them. Let me call that beta. Oh, no, okay. Let's call that gamma, and let's call that beta. Okay. So let's stare at that metric for a second. So the first thing that you should notice is that there's still some freedom under the change of coordinates that I could use to put this metric in a simpler form. So I have chosen the t and the angular variables theta and phi to make the symmetries under time translation and rotation manifest. But rho is just some other coordinate that appeared here. And I could always take rho to some function of rho and see if that would allow me to put the metric in a simpler form. So I could always define some new coordinate, which is a function of rho, and take that to be this extra coordinate instead of rho. That's just freedom to describe my metric in whatever coordinate system I like. So let's stare at this boxed metric I've written here and see if we can think of a nice choice for rho, a nice choice for a new variable that might be physically intuitive. Well, what do we have here? We have here a two-sphere, and we have the function e to the 2 gamma multiplying that two-sphere. So let's remember what flat space looks like if you write it in spherical coordinates. In spherical coordinates, Minkowski space has the following metric: minus dt squared plus dr squared plus r squared d omega squared, where r is a radial coordinate and d omega squared is the metric on the two-sphere. So let's compare that to this boxed metric that I wrote up here. So we can see that one particularly nice choice for the variable, the extra variable that my metric depends on, would be if I chose a variable r which is equal to e to the gamma. So let's choose a radial coordinate r, which will be some function of rho, which is equal to e to the gamma. And then in these coordinates, so in the r coordinates, what will the metric look like? The metric will look like e to the 2 alpha dt hat squared plus some function of r times dr squared plus r squared d omega squared. If I wanted to, I could call this beta hat instead of beta, because it's not equal to the same beta that I wrote above. Let me just be a little more explicit. So if r is equal to e to the gamma, where gamma is a function of rho, that means that dr is equal to, let's call it d gamma by d rho e to the gamma times d rho. That's just the chain rule. So the e to the 2 beta d rho squared that appears in the metric, what is that? That's e to the 2 beta times d gamma by d rho e gamma to the minus 2 times dr squared. And this is the function that I will call e to the 2 beta hat. So what have we done? What we have done here is we've just changed our radial variable from rho to r so that our radial variable has a nice physical interpretation. It's the thing that determines the size of the 2-sphere. And this then will be the metric that we will try to study, and we will try and solve the equations of motion in order to determine alpha and beta hat. Are there any questions on that? It's always important to try and use your freedom under the change of coordinates to write your metric in as simple a manner as possible. I could have also, for example, chosen to set the coefficient of d rho squared equal to 0. That would also be another perfectly legitimate choice of coordinates. Or I could have set the coefficient of dt squared to be whatever I liked. And those coordinate choices would all be fine, and at the end of the day, they would just give me the same answer for the Schwarzschild solution, but written in a different coordinate system. I've chosen this coordinate system because it will make the similarities of our metric with flat space quite apparent. Any questions before I continue? Okay. So let's rewrite this metric here. So ds squared is minus e to the 2 alpha dt hat squared plus e to the 2 beta hat dr squared plus r squared d omega squared. I've dropped the hat because I'm a lazy person. I could have just as easily called my original beta hat and then this beta, so let's forget about the hat. Okay, and let's give ourselves some nice room. Okay, so now what we need to do is compute the Ricci tensor of this spacetime and set it equal to 0. As I said, I'm a very lazy person. So what I'm going to do is assign this to you as a problem on your next problem set, and I will just tell you what the answer is. What is the answer? So in the next problem set, you will show that the Ricci tensor takes the following form. You know, it's not just that I'm a lazy person that I'm going to make you do the calculation. It's perhaps the most important computation of the Christoffel symbols, Riemann tensor, and Ricci tensor in the subject of general relativity, and it would be selfish of me to keep it to myself, so I will invite you to do it. The only non-zero components of the Ricci tensor are the diagonal ones. So RTT, or RT hat T hat, is e to the 2 alpha minus beta times alpha double dot plus alpha dot squared minus alpha dot beta dot plus 2 over r alpha dot. The RR component of the Ricci tensor is minus alpha double dot minus alpha dot squared plus alpha dot beta dot plus 2 over r beta dot. And the final component is r theta theta, which is e to the minus 2 beta, r beta dot minus alpha dot minus 1, all plus 1, and r phi is just equal to sine squared theta times r theta theta. So here, alpha and beta are the two functions that appear in the metric, and dot denotes d by dr. So dot is d by dr. Okay, so if we want to solve Einstein's equations, we just need to set this whole mess equal to 0. Now, if you stare at these equations for a few minutes, then you'll see that, in fact, the easiest way to solve the Einstein equations is not to just set all of the individual components of the Ricci tensor equal to 0, but to try and find certain linear combinations of the components of the Ricci tensor where these differential equations will take a particularly simple form. So let's look at the TT and the RR components of the Ricci tensor for a minute. You can actually see that they have a very similar structure. So in particular, if we set R mu nu equals to 0, then that means that any linear combination of RTT and RRR will have to be equal to 0. So let's consider the following linear combination. So let's take RRR plus e to the minus 2 alpha minus beta times r t hat t hat. So that's got to be equal to 0. And what is that? Well, you can see I've chosen that so that the alpha double dot minus alpha dot square term in RRR gets canceled out. And what do you get? You get 2 over r times alpha dot plus beta dot will be equal to 0. Or, put more simply, this says that alpha will be equal to minus beta plus a constant, where c here is some constant of integration. Okay, let's go back and stare at our metric and see what this means. So our metric was minus e to the 2 alpha, which is e to the minus 2 beta plus 2c times dt hat squared, plus e to the 2 beta times dr squared plus r squared d omega squared, where c is just some constant. So you can see now why I've been a little neurotic about calling my time coordinate t hat instead of t. Because at the end of the day, I would like to absorb that constant c into my definition of the time coordinate. So what I will do is define a new coordinate. So let's use a new time coordinate, which I will call t instead of t hat. T will be equal to e to the c times t hat, so that dt squared will be equal to e to the 2c times dt hat squared. And in these coordinates, the metric is minus e to the minus 2 beta dt squared plus e to the 2 beta dr squared plus r squared d omega squared. Yes?
This might be too simplistic, but you already rescaled your distances, right?
Yes.
So if you want to keep c equal to 1, how can you also rescale time?
Well, I didn't just rescale my distances. I took some whole new distance coordinate. I took some whole new radial coordinate. But I didn't do anything to the time coordinate. Right. I should emphasize that I'm not multiplying time by a function of r, just multiplying it by a constant.
But so, like, if you double time, then it doesn't, like, keep c equal to 1, then you have to have...
So I'm setting c equals 0, not 1. But yes, go ahead. Rescaling time by an overall factor will shift what I called alpha by a constant. If this isn't clear, I encourage you to go through it again on your own. Maybe I'm not. Yeah. What can I say? I'm just choosing a new time coordinate to put the metric in as simple a form as possible. This is an important lesson to internalize, which is that in these sorts of computations, you're never going to get anywhere unless you use the freedom to change coordinates in the most intelligent way possible. And you want to always be constantly trying to find coordinate systems which make your life easier. You know, I first chose my radial coordinate to be something convenient. Now I've chosen my time coordinate to be something convenient. This is a lesson that will be beaten into you over the course of the semester. Beaten into you in the kindest, friendliest way, of course, but beaten into you nonetheless. Any other questions? Okay. So now let's look at the final equations of motion. So let's just look at the r theta theta equation of motion. So in these coordinates, alpha was equal to minus beta. So r theta theta, so that was e to the minus 2 beta times r times beta dot minus alpha dot minus 1 plus 1 had to be equal to 0. So in these coordinates, alpha is equal to minus beta. So this says that e to the minus 2 beta times r times 2 beta dot. So that's, what is that? That's 2 beta dot r minus 1 plus 1 is equal to 0. Let's stare at that equation for a second. At first sight, this is not the easiest equation to solve. It's a first-order differential equation, but it's a nonlinear differential equation for beta. And nonlinear differential equations are always hard to solve. Except this one. This one's actually pretty easy to solve. Well, any first-order differential equation can be reduced to an integral. In this case, we don't even need to be that highfalutin. We can just stare at this equation and write down the answer. So let's start staring. Okay, well, what's the first thing that we should do? Well, let's move that plus 1 onto the other side of the equation. And let's write this as e to the minus 2 beta times 1 minus 2r beta dot is equal to minus 1. Plus 1. I've multiplied through by a minus sign. Or e to the minus 2 beta minus 2r beta dot e to the minus 2 beta is equal to 1. And what is that? That's just minus r d by dr, plus r d by dr of e to the minus 2 beta will be equal to 1. Right? Because what is d by dr of e to the minus 2 beta? It's e to the minus 2 beta times minus 2 beta dot. Okay? And then let's stare at the left-hand side of this equation. What is that? That is d by dr of r e to the minus 2 beta. Right? So what does this tell you? This says that r times e to the minus 2 beta is equal to r plus a constant of motion, a constant of integration with dimensions of length, right? Because it is added to something, it's added to r. And I will call that constant of motion minus capital R. So R is a constant of integration with dimensions of length. Or, writing this a little more simply, e to the minus 2 beta, which is the function that appears in the equation for the metric, is 1 minus a constant over R. So what is our metric? Well, e to the minus 2 beta was the coefficient of dt squared. So it's minus 1 minus capital R over R times dt squared. The coefficient of dr squared was e to the 2 beta, not e to the minus 2 beta. So we have 1 minus capital R over R inverse times dr squared then plus the angular piece, r squared d omega squared. And this is the famous Schwarzschild solution of the vacuum Einstein equations. So this is the Schwarzschild solution. The parameter r here is just a constant of integration which appears in the equations of motion. It has a name. We usually call it r sub s, and it's known as the Schwarzschild radius. So it's useful now to compare this to the Newtonian metric that we started this lecture with, describing the gravitational potential around a static spherically symmetric object. But before I do so, let me pause and see if there are any questions. No questions? Yes.
So, the Schwarzschild radius, is that
We will, in just a second, I will tell you exactly what the Schwarzschild radius is. It is a constant.
but it's fixed, right?
We will discuss exactly what the Schwarzschild radius is in about 30 seconds. Are there any questions on the derivation of this solution? So what have we seen? We have seen that the metric around a static spherically symmetric object involves a constant, and only one constant. So if you think for a second, you can probably guess what the physical meaning of that constant is. But yes, there's a question.
In the beginning, when we first wrote the equation for our metric, we used e to the alpha, e to the beta, and e to the gamma.
Yes.
How did we guess that would be more convenient than something else?
I used e to the alpha. Of course, I didn't need to use the exponentials. I could have written down, I used the exponentials because the exponential of something has the nice property that it's always positive, right? So let's go and look at what I started out with. I had, for example, a minus e to the 2 alpha dt hat squared because I want t to be a time-like coordinate. So I want its coefficient to be negative. And so I put here minus times the exponential of something. So minus something that's guaranteed to be positive. Of course, I didn't have to do that. At the end of the day, I could have chosen just alpha, beta, and gamma instead of e to the 2 alpha, e to the 2 beta, e to the 2 gamma. I would, of course, get exactly the same answer. I chose this because it made my equations particularly simple. But there was no particularly deep reason.
What do you guess? What would be the simplest thing to use for?
Well, you've done this before. That's the answer. If I used alpha, beta, and gamma instead of the exponentials, it wouldn't have been that much more complicated. I would have just had alpha dots over alpha floating around everywhere instead of alpha dots, right? That's what happens if you take alpha to the log of alpha. You get alpha dot over alpha. Okay, not too much harder. But I did this with the malice of forethought, or whatever the appropriate phrase is. And it wasn't, I want to find, I don't want to spoil the surprise when we start discussing black holes, so I don't want to comment too much about this. But I chose very carefully my coordinate system so that the t direction would be time-like. I've explicitly chosen here to multiply t times something which is manifestly negative, so that it's a time-like direction here. But we will see soon enough that there are also parts of the space-time that have where the coefficient of dt squared is positive instead of negative, and that has a very interesting physical interpretation, which we will discuss. But because I have chosen this particular form for the functions appearing in my metric, I have ended up with a solution for the metric which only describes a particular patch of the space-time geometry. It only describes one region of the space-time geometry. You know, as we discussed before, there are many spacetimes for which there is no global coordinate system that covers the entire geometry. And in particular, if you're solving some set of equations of motion for some spacetime, there's no guarantee that the coordinates that you just happen to have chosen will be coordinates that cover the entire spacetime. I have presented this derivation, which has led us to the Schwarzschild spacetime in what are known as the Schwarzschild coordinates. But there are other coordinates that we will discuss that describe the spacetime that are useful for other purposes. I have focused on these coordinates because it makes the physical interpretation of this metric as the metric of a static spherically symmetric object quite clear. So let's understand why that is. So what we want to do is compare this with our Newtonian expectation that the gravitational potential is equal to minus, so in Newtonian gravity, the gravitational potential was equal to Gm over R. That's the Newtonian potential. And let's compare, and let's remember that a weakly curved spacetime describes Newtonian gravity. It matches up with our expectations from Newtonian gravity if the time component of the metric is identified with 1 minus 2 phi. This is what we concluded about 2 weeks ago when we decided that Newtonian gravity was, in fact, a theory of objects moving on geodesics in a space-time which was close to but not exactly flat Minkowski space. So if you compare this to this, you see that the weakly curved geometry that describes the metric around a spherically symmetric object has GTT, which is equal to 1 minus 1 minus 2 GM over R. So that gives us a physical interpretation for the Schwarzschild radius that appeared in our metric. What is the Schwarzschild radius? The Schwarzschild radius is nothing more, nothing less than the mass of the object that we're describing. In particular, it's twice Newton's constant times the mass of the object. Now, I invite you to check that in units where c is equal to 1, Newton's constant times mass has units of length. And so, indeed, the Newton's constant times the mass of an object is something which has dimensions of length, and it should be regarded as the gravitational length scale associated to a massive object. So just on the basis of dimensional analysis, we could have concluded a long time ago that in general relativity, if you have an object with mass m, then the typical length scale that describes the curvature of space-time due to that object should be Newton's constant times the mass. There's really nothing else it could be, just on the basis of dimensional analysis. And now we have seen exactly what the metric looks like. Let me write it down for you again. In the presence of an object with mass m. And we have seen that, in fact, our weakly curved approximation was not so far off in this case from the actual answer. Indeed, the coefficient of dt squared is not just approximately given by 1 minus 2 phi, but it's actually given by 1 minus 2 phi. The only difference from our weakly curved approximation is that now we trust this metric even when r is of order the Schwarzschild radius and the geometry is strongly curved. And also we have discovered that there is a coefficient of dr squared as well. So what I would now like to do is just make a few comments on the structure of this metric and tell you a little bit about its physical interpretation before, at the end of class and continuing into next class, we will study in detail the physics of objects moving in the Schwarzschild geometry. Okay. So let's just stare at this metric for a few minutes. Well, the first thing, and one of the most important things that we notice about this metric, is that at large radius, as r goes to infinity, this metric becomes Minkowski space. In particular, when r is very large compared to the Schwarzschild radius, this metric is very, very close to flat Minkowski space. Intuitively, of course, that makes perfect sense. It means that if you're very far away from an object, then the gravitational effect of that object is very small. The next thing which is obvious about this metric is that something very funny happens when r is equal to the Schwarzschild radius. As r approaches the Schwarzschild radius, what happens? Well, the coefficient of dt squared goes to 0, and the coefficient of dr squared goes to infinity. Okay, I told you that we, generally speaking, a metric should have the metric should be a invertible matrix, and in particular, it should have eigenvalues 1, 0, 0. But if some components of the metric are going to 0 and some are going to infinity, then that appears not to be the case. So the fact that as r goes to r Schwarzschild, something funny happens, well, there are two possible things that could happen when the coefficients of the metric blow up or go to 0. One thing that could be going on is that the metric is sick in some way. The other thing that could be going on is that the choice of coordinates that we are using to describe the metric is sick in some way. And it turns out, as we will investigate in great detail, that in fact it is the second which is occurring here rather than the first. And so it turns out that the fact that some of the components of the metric are 0 and others are divergent is a consequence of the fact that our coordinate system is breaking down at r equals to rs, not some signature of the sickness of this metric in general. So when r is equal to rs, the coefficient of dt squared is going to 0, which means that the direction which had become time is becoming a null direction, a light-like direction. So there's a special name that we give to this location where the time-like direction becomes null. We call this the event horizon of the solution. Why it's called the event horizon and what the physical interpretation of those words are is something that we will return to in great detail in our study of black holes. But for the next week or so, I wish to focus on scales that are large compared to the Schwarzschild radius so that we can understand some of the experimental tests of general relativity before diving into the subject of black holes. But let me make one final comment on the behavior of this metric at small values of r, just because it's something that we can clearly see from the metric. So not only does something funny happen at r being equal to the Schwarzschild radius, something funny also happens when r goes to 0. So in this case, the coefficient of dt squared is going to infinity, and the coefficient of dr squared is going to 0. And again, this could be due either to something sick happening to the metric at this point, or it could be due to the fact that our coordinate system is breaking down. And in fact, at the point r equals 0, it turns out that the first of these is happening, not the second. So in fact, the metric is really becoming singular at this point. And this is known as the singularity at the core of the Schwarzschild solution. Now, at first sight, you shouldn't necessarily be surprised that there's a singularity at the center of this solution. If you look in Newtonian gravity, and you stare at the Newtonian potential, gm over r of a static spherically symmetric object, the Newtonian potential diverges at r equals 0. That's not a signature that Newtonian gravity is a bad theory of gravity. It's just a signature of the fact that you shouldn't really be using that solution at r equals 0, because realistically, objects whose gravitational fields you're studying aren't point masses. They don't have all of their mass focused at the point r equals 0, but rather they have some mass distribution which behaves in some reasonably smooth manner. So, for example, in Newtonian gravity, the fact that at r equals 0 the Newtonian potential blows up just means that you shouldn't be using the gm over r solution of Newton's equation at the center of the sun. Instead, you should be solving Newton's equation with some mass terms, and you would get some nice, smooth, reasonable behavior at r equals 0. And in many cases, this is exactly the situation in general relativity. If you're studying the metric around a star, for example, then the Schwarzschild solution is a perfectly good description of the behavior of the geometry of spacetime outside of the star. But inside of the star, you need to study not the vacuum Einstein equation, but Einstein's equation coupled to matter. And you would need to come up with some model for the matter of the star. It's like Groucho Marx said. What did he say? He said, outside of a dog, a book is a man's best friend, and inside of a dog, it's too dark to read. So general relativity is just like that. However, there is one case where the event horizon and the singularity need to be taken seriously, and that's if you have an object which is so massive that the Schwarzschild metric is a good description of the geometry, even all the way down to the Schwarzschild radius. That's something that we'll return to later on, but for the time being, I would like to focus on objects I would like to focus on the study of objects whose radius, whose physical radius, is much larger than their Schwarzschild radius. So it then behooves us to actually calculate the Schwarzschild radius for all sorts of objects of interest. So, for example, I invite you to just go plug in the value of the speed of light and Newton's constant and calculate the Schwarzschild radius of the Earth. You'll find that it's about 1 centimeter. Likewise, the Schwarzschild radius of the Sun is around 3 kilometers. And as you increase the mass of an object, the Schwarzschild radius increases linearly. So this is just a reflection of the fact that the Sun is, 300,000 times more massive than the Earth. Now, of course, the Earth is much bigger than 1 centimeter, the sun is much bigger than 3 kilometers. So indeed, if you're studying vanilla solar system physics, then you never need to worry about these apparent pathologies of the Schwarzschild metric at small radius. So for quote-unquote normal objects, the horizon and the singularity are irrelevant. Indeed, for the first 50 years or so of the study of general relativity, they were ignored completely. They were regarded as pathologies of the Schwarzschild solution, which were not physically relevant. And it was only in, really starting in the 50s, I guess, that they were started to be taken seriously, and the subject of black holes became a subject of legitimate study. Let me make one final comment about the Schwarzschild solution. So, we have shown that the Schwarzschild solution is the unique solution of the equations of general relativity if we have a rotation symmetry, a time translation symmetry, and a time reversal symmetry. In fact, although I won't prove it to you, a much stronger statement is true. In fact, the Schwarzschild solution is the unique solution of general relativity with spherical symmetry. In particular, if you impose spherical symmetry, then you can show that the metric is necessarily also going to be static, and it will have no off-diagonal terms, and so it will reduce to the Schwarzschild solution. I should actually remark there's one other assumption that goes into this. You also have to assume that the metric is asymptotically approaching Minkowski space and is smooth everywhere between the horizon and Minkowski space. But once you assume this, then you can show that the Schwarzschild solution is the unique solution with spherical symmetry. And this is a result which is known as the Birkhoff theorem. It's actually pretty easy to prove. You just need to study these differential equations as a function of both t and r, and then manipulate them. It's a slightly more complicated set of manipulations than the one we've done. It's contained in your textbook, I think. I won't bother to do it here. I don't think the details of that proof are particularly important for our purposes, but it's a good thing to know. I think one interesting interpretation of the Birkhoff theorem is the statement that in general relativity, every spherically symmetric object is described by one parameter and one parameter only, which is the mass. When we touch on the subject of black holes and black hole thermodynamics, if we have time to discuss such things at the end of the course, then this will have a very interesting interpretation. Okay. So the question that we would now like to ask, having invested this time and energy in the derivation of the Schwarzschild metric, is what physics looks like in the Schwarzschild background. And in particular, we would like to ask how geodesic motion looks in the Schwarzschild spacetime. We would like to ask what the effect of the Schwarzschild geometry is on gravity, on the motion of objects in the presence of a spherically symmetric object. In order to do that, we will need to solve the geodesic equations in the Schwarzschild background. That's something that I would like to start doing today. I probably won't finish it today. Let me pause and see if there are any questions before I dive into this. Yes?
Could you add
That's a very good question. The question was, we have here a solution describing a single object. You might think it would be relatively easy to describe the space-time around, say, two objects. Now, the equations of motion of general relativity are nonlinear, which means you can't just add two metrics together to find a third metric. So that means that, in general, this is going to be a very difficult task. And in fact, it's a task that, except in a few very special circumstances, can only be accomplished numerically rather than, or in some approximation, rather than analytically. Why is that? Well, if you have two very, very widely separated objects, then you would expect that near one of them, the metric is approximately Schwarzschild, and near the other, the metric is approximately Schwarzschild. And maybe you could try and match them together in some way. And in some cases, that would be a good approximation. But in general, if you have two Schwarzschild black holes, then they will attract one another. And so, in fact, Schwarzschild black holes. If you have two massive objects, then they will attract one another. And so there is no static solution describing two black holes that are just sitting statically. The only way you could find such a static solution would be if you introduce some other stuff which would cancel the gravitational attraction. So, for example, there are certain black holes where there are certain objects where it's easy to write down the metric of what we would call multi-center objects or multi-center black holes. But in general, this is something which is very difficult to study. So in a lot of interesting questions for astrophysics, for the study of gravitational waves, for the study of structure formation, we're actually interested in questions of, say, two stars, a binary star system, where the stars are in orbit around one another. That's something that we don't know how to write down an exact metric for. It's something we can only study approximately or numerically. And the subject of numerical relativity is very much a subject of active research. And in fact, in the last decade or so, there's been a great deal of progress in this subject. There are various special cases where we can write down exact answers, but they all involve some sort of additional assumptions. So that's a good question. Yes. There was another question.
Okay, so the limit system we're using to describe the Schwarzschild spacetime breaks down at the event horizon.
Yes.
Is it still a valid description of spacetime within the event horizon size?
Yes. But the interpretation is quite different. So in fact, if you look at the metric that I wrote down, well, I don't want to spend too much time talking about this because we'll come to the subject of black holes eventually. But if you look at the metric that I wrote down, this is a perfectly decent looking metric when R is larger than Rs. It's also a perfectly decent looking metric when R is less than Rs but larger than 0. One has to interpret appropriately that metric because in this case the coefficient of dt squared is positive and the coefficient of dr squared is negative. So there's a sense in which when you're inside the event horizon, the time and the space coordinates have interchanged roles. T is a spatial coordinate and R is a time-like coordinate. For that reason, these are not the coordinates that we most typically use to study the inside of the horizon. They're a little confusing. You need to be very careful when you analyze physics inside the event horizon of the black hole. That's something that we'll turn to in about a week and a half. Yes?
So in the beginning, we assumed time translation symmetry.
Yes. Yes.
And we got a time component that was the same as the one for a week.
Yes.
So does this mean that these two symmetries only hold for a week currently?
No. It means, so we're just assuming that these two symmetries hold in general, and it just happens to be a nice coincidence, and I think it's nothing more than a coincidence, that the dt squared component of the metric looked exactly like 1 minus 2gm over r. That was just a coincidence. We knew that's what it had to look like at large r, where space-time is weakly curved. And it just happens to be that that's what it looks like at smaller r as well. That, I think, that's just an accident, that the equations of motion are relatively simple with so much symmetry that this is just what it is. But you shouldn't take this as a general fact of life. Any other questions? Okay. Well, it's 10:23. I don't want to start a discussion that I won't be able to finish. And indeed, the discussion of the geodesics and the Schwarzschild background is something that I think is worth doing in a great deal of detail. So I don't want to start that now. So I'll just go ahead and start that next class. Maybe we have time for one or two more questions then. Yes?
So if you get rid of time translation, do you end up with spherical gravitational waves?
No, that's actually, this Birkhoff theorem that I've referred to says that essentially if you assume spherical symmetry, then you have time translation symmetry. Yeah, it says, so in other words, the Birkhoff theorem says that spherical symmetry implies the Schrödinger solution, Schwarzschild solution, which has time translation symmetry. So what does that mean? That means that a spherically symmetric object cannot emit gravitational waves. Okay, that's an important, so a spherically symmetric object cannot emit gravity waves. That actually is something that should, morally speaking, not terribly surprise you if you remember your courses on electromagnetism. Because if you remember electromagnetic waves, you can't have a time-varying monopole moment. So spherical symmetry means that you only have a monopole moment in the language of electromagnetism. And electromagnetic radiation, the leading term, comes from the time variation of the dipole moment, not the monopole moment. And so that means that there's sort of no such, you can't have a time-varying monopole moment. And roughly speaking, the same thing is true in general relativity. In fact, it turns out that in general relativity, not only can you not have a time-varying monopole moment, you can't have a time-varying dipole moment either. When we come to the subject of gravity waves, that's something that we'll discuss. So yes, a spherically symmetric object does not emit gravity waves. And it implies time translation, yes. This is one of the reasons why gravity waves are often hard to detect. As you probably remember from electromagnetism, quadrupole. So if the leading contribution to gravity waves come from a time-varying quadrupole moment, not a dipole moment, then that's going to be even higher, more suppressed than the corresponding quantity in electromagnetism. So that's why gravity waves are only emitted by objects that are very, very far from spherical symmetry, morally speaking. Things like colliding black holes, neutron stars, stuff like that. Other questions? Yes.
What's the April 15th colloquium about?
It's about black holes.
Oh.
Any other questions? By the way, yeah, you should all be going to the colloquium in general. But I'm going to give you, a little bit of extra credit if you go to the colloquium on April 15th. It's on black holes. It's Friday. It's April 15th. But, it's like a million years from now. Any other questions? Okay, I'll see you on Monday.